All right, let's see if this works. We're going to try and make an answer key and walk through a discussion for activity 7.1, which introduces periodic functions. So if you've read the top paragraph, our first job is to try and draw a picture of this Ferris wheel. So all I've done is I've drawn a circle, and the circle shows that the ground level, that's going to be a height of 0. I've noted up top that our radius of this circle should be 250 and the diameter 500. If we're told that we have a rotation time of 20 minutes, what I'm going to do is I'm going to assume counterclockwise rotation, and that's going to make it consistent for all of us. So counterclockwise means we'll start and we'll travel around in that direction. So at time 0, time 5, time 10, 15, and 20. So that would break up the 20-minute rotation time into 4 equal parts, so we get to 5, 10, 15, 20, etc. Our next job is to fill out a table of values. So at time 0, I filled in for us already that we were at the ground level of 0. Now, notice in 20 minutes, we went from 0 up to a height of 250 by the time we're at the 5-minute mark, up to a height of 500, that's the top of our Ferris wheel, back down to 250, and then back to a height of 0. Now if we extend this for another 20 minutes, you can see 0, 250, 500, 250, and 0. The pattern in the output column will repeat based on heights repeating, time 0, 5, 10, 15, 20, 25, 30, 35, and then of course 40 minutes would put us back at the bottom of the Ferris wheel. Now, we were asked to plot points and approximate a curve that might join them. So you'll notice down below, all I have done is I've gone ahead and I have plotted those points and then tried to connect them with a smooth-ish curve. The curve is not perfect. What I do want you to notice is that if you plot those points and actually tried to lay down a ruler, you'd have a hard time connecting a single straight line from here through these 3 points. They're not going to fall on a straight line necessarily, but that's okay. We can just put a little bit of concavity here, a little bit of concavity here, so on and so forth, and that will give us this nice looking curve. Now, related to this curve, I want to talk about a couple of definitions, so I'm going to slide up here. So, the first definition will be for a period. And a period, or a periodic function, what we want to think about is any function where the output values repeat. Here we see this in 2 places. We see it on the table, our heights of 0, 255, 250, 0, 0, 255, 250, 0. Right? Every 20 minutes we see that pattern repeating. And then of course on the graph we can see we started at 0 up to 250, up to 500, back to 250, back to 0, up to 250, up to 500, down to 250, back to 0. So we've got this repetition. So a period is going to be a time interval where our outputs repeat. In this case, our period, we typically denote that P, will be 20 minutes. Now, a couple other pieces of vocabulary, what we want to think about here will be, well, shoot, let's start here. Our dotted line at 250, we're going to call that a midline at an H value of 250. And of course, I'm using H because our output function is called h of t, so at h equals 250 seems like a reasonable way to describe that. And then last but not least, we're going to describe an amplitude of this curve. And that is the distance, the vertical distance between our midline at 250 and then our peak, of course, that's at 500, or the distance between our midline at 250 and that low point, that minimum value, which is, of course, at 0. So we describe an amplitude. Generally, we do that with a capital A, and we'll say our amplitude is 250. Now for a period, it's worth noting there is a slightly more formal definition, and that definition looks like that. And of course you'll read about that in our textbook, that T plus C equals F of T. Notice, of course, this is an inside change, so we can think about it as a horizontal shift. In this particular problem, if we had H of T plus 20 minutes, we're going to get back to the same height as we started. So that's a function notation definition for a period, and that's kind of neat. Last but not least, related to this problem, let's go ahead and describe our domain and range. Our domain would be T is allowed to be any real number. If you haven't seen that notation, this is an alternative for writing a compound inequality that would say negative infinity less than T less than infinity. It's a shorthand notation. I prefer it. It's a little cleaner. Notice if you choose to write a compound inequality here, you cannot, of course, underline the inequality notation whenever you have infinities. It's impossible to reach infinity, therefore we can never underline those. Last but not least, let's capture the range of this function. And here, our range values, our height values, vary between 0 and 500. Notice in this case we actually reach a height of 0. That was at time 0, 20, and 40. And we certainly reach our maximum height of 500. That was at time 10 and 30. So if I were to write this with a compound inequality, I would write 0 less than or equal to h of t is less than or equal to 500. Another way to write that, which I'll start to use and you'll hopefully get a little more comfortable with over time, is we'll say h of t is an element of the closed interval 0, 500. What you want to notice here is that I am using squared bracket notation. Squared brackets in this interval notation correlate with our less than or equals to. So that's our notation for the front page. Let's go ahead and we can take a look at example number 3 on the next page. Now, in the next example, we're asked how would our graph change if we make some changes to this situation. Of course, I've given a little hint here suggesting we would make a table. The loading platform is at the 3 o'clock position on the Ferris wheel. So what we'll do is we will assume that everything else remains the same. So I'm going to go ahead and draw a quick little Ferris wheel. And here is where we're going to put our time value of 0, time value of 5, 15, and our time value of 20 minutes. I'm a liar. We'll call that time value of 10, 15, and my apologies, that puts us back at the 3 o'clock position at our time value of 20. And of course we could continue this indefinitely if we were to choose to. Now I'm going to go ahead and make that table of values, and that table of values will help us create our graph here in a second. Oh, and I think I even had it written for us already. There we go. And looky there. This is what we've got. We've got a time value of 0. I want you to notice we would be at a height already of 250. Time value of 5 would be at the peak for 500. 250 back to 0. And then at 20 minutes we've made our way to the initial height here, which is 250 feet above ground. I've gone ahead and I've plotted some points. I'm going to scoot over so we can see it real well. Started at 250, up to 500, back to 250, down to ground level, back to 250, so on and so forth. Notice that we go ahead and repeat that pattern, so we appear to have that periodicity a second time. Couple of observations. This graph appears to be shifted horizontally compared to our initial graph. Couple things we should talk about. We have that midline again at 250. Notice midline at 250. Our amplitude, that vertical distance between the midline and the peak, is 250. Notice again the midline down to the minimum value here is also a distance of 250. Our period is 20 minutes. And when we look at graphs, that's a way for us to notice the period, right? We see this repeated pattern, midline, peak, midline, valley, midline, repeat, so on and so forth. So every 20 minutes we would see an exact duplication of this pattern. So we get a little change to our problem. Now if we slide down and start talking about part B, the Ferris wheel, we're going to expand it to a 600-foot diameter, and we'll go back to that 6 o'clock loading position at the bottom of the Ferris wheel. So I've drawn a picture again, just a real rough sketch of a Ferris wheel, times 0 times 20. So if we're keeping a 20-minute rotation time, times 0, 5, 10, 15, 20, 25, 30, 35, 40. So we would have this repetition as we go around. I've gone ahead and made a table of values over here. At time 0, we're at the bottom of the Ferris wheel, so our height would be 0. At time 10 minutes, we're all the way up at the top. In this case, that diameter of 600 would represent our peak, our maximum height. At 5 and 15, we're at the 3 o'clock and 9 o'clock positions respectively, so our height would only be half of that, or 300 feet above ground. And then at 20 minutes, we're back to ground level. So I've gone ahead and I've plotted those points, incorporated a little bit of concavity again, and here I have off to the side, let's scoot over so I know you can see it, we have a period again of 20 minutes. Here we have a different amplitude. Our amplitude is 300. That's our distance from the midline up to the maximum, the midline down to the minimum, of course, and of course our midline is at that height value of 300. It's worth noticing that when we have expanded our diameter graphically, this is very much like our problem from example number 1. The big difference, of course, here is that we have stretched our graph vertically. If you recall from Math 111, a vertical stretch would be a transformation of that form A f of x, where A takes the output values and then multiplies them, makes them taller. In this case, our A value would be bigger than 1, creating the expansion. Last but not least, let's get to excuse me. All right. Now, last but not least, our Ferris wheel has a 600-foot diameter and takes 30 minutes to complete a rotation. We'll keep that loading at the 6 o'clock position, and we're going to show 2 rotations on the graph. So if I've got a 30-minute rotation time, when I built my table, what I want you to notice is I had my 30-minute rotation time, so height of 0 at time 0, height of 0 at time 30. I knew that at 15 minutes I would be at the top of our Ferris wheel, so that had our maximum height of 600. Now, one thing that was a little tricky here for me is I had to figure out what the heck time values went along with the 3 o'clock and the 6 o'clock position. Notice that 15 cut that in half, and that gave me the 7.5 minute time value, and then 7.5 on top of 15 minutes got me a 22.5. So I ended up scaling my input table values by 7.5 in order to get quarters. And that's quarters of the 30-minute rotation. So I've gone ahead, created a graph here. What we want to notice is that this slowdown has expanded our graph horizontally. So in the previous example, you'll notice it took 40 minutes to complete 1 full cycle, 2 full cycles. Here, it's taken 30 out to 60 minutes to complete 2 full cycles of this graph. Now that we will refer to shortly as a horizontal stretch. So we've taken the graph and we've effectively pulled it away from the y-axis, the vertical axis. Last but not least, you should notice that we have our period is 30 minutes. Our amplitude, again, that distance midline to maximum, midline to minimum, is 300, and our midline value, I should put those in a different order moving forward, our midline is at 300, halfway between the peak and the valley. Let's proceed to page 3. On page 3, of course, the graph below describes our height, where h is in meters, t is in minutes, and then we're going to answer some questions based on the graph. So the first question asks us how long it takes to complete a rotation. So one rotation, what we want to recall from our previous work is we're looking at the period really. And here you can see that we've completed a full rotation around the circle. We started, went down, back up to the middle, up to our peak, back to the middle. So that's where I see a period, and that would give us a 4-minute period for this particular function. The diameter of the wheel every single time shows from ground level, height of 0, up to that maximum height of 40 meters. So I know that the diameter was 40 meters. You might also notice that the radius, we could have specified that the radius was 20. Of course, how much time are we riding this wheel? It looks to me like 10 minutes. That's where our graph stopped. The midline is at a height of 20. What is the practical meaning? Well, there are a couple things you might have said that. That's the height of the center of the wheel. You might have said this is the radius. You might have said that is the height when we loaded onto the Ferris wheel. A couple different things we could say there. The period is 4 minutes. That's starting out to 4 minutes, 4 to 8, so on and so forth. So we could describe that as our rotation time as a practical meaning. And then the amplitude would be 20 when we see our midline at 20 dotted in here, 20 down to the floor, right, ground level. Of course, that's a difference of 20, 20 up to our maximum height. Again, that is a distance of 20. Amplitude, I will associate that with the radius of our wheel. Let's move on. Page 4. On page 4, notice the vertical position of the seat on the Ferris wheel is shown, and we're given by the graph. So here we had a graph provided, and I noticed that we took 20 minutes, and we started at a midline and went up. So midline, I went up, back down, back up, so on and so forth. So you'll notice the orange highlighted circle segment represents this orange highlighted piece of my graph. From the peak back down to the midline is shown in purple, and then I've dropped back down and back up. Couple of things. Label on the wheel where the seat is at time 0. So we are at time 0 at that 3 o'clock position. How long does it take for the wheel to complete a revolution? We can see from our graph that would be a 20-minute time period again. Shading, we've done that. Shading, we've done that. How many revolutions are shown? Looks to me like we had one full revolution and then another half of a revolution shown there. Where is the seat at 30 minutes? 30 minutes, well shoot, if we dig around, 30 minutes. We're at the midline on our way down, so that would have been 30 minutes over at that 9 o'clock position. Label on the Ferris wheel and give parts correspond to. Period is 20, amplitude is 10, that's our radius again. Height of the center is at that midline of 15 in this case. Notice also in this problem we have this across the bottom where we have a 5 feet difference between the minimum value on our Ferris wheel curve, our height curve, and the ground level. That suggests to us that the loading platform, or that the bottom of the wheel stays minimum 5 feet above ground level. Last but not least, we get to page 5 of handout number 1, and apparently this is about 20 minutes in length. What I want you to notice in example 6 is we have a repetition in the output values 5, 3, 1, 3, 5, 3, 1, 3, 5, 3, 1, 3, so on and so forth. We could extend that pattern. The pattern repeats between 5 and here, so our period would be 4 minutes. Our maximum value is 5. Our minimum value is 1. So halfway between 5 and 1 gives me a midline value at 3. An easy way to think about that would be an average. Amplitude is 2, so if our minimum is at 1, our maximum is at 5. Midline at 3. From 3 up to that maximum is a distance of 2. From 3 down to that minimum value is again a distance of 2. So that gives us an amplitude. You'll notice in the second table, it has a nice pattern, of course. That's not periodic. We should recognize that as linear. Down 2, down 2, down 2, so on and so forth. Last but not least, non-periodic. We don't see the outputs repeating. It's got a cool little shape associated with it, but it's definitely not repeating. We reached our peak once and then we never attained that height again. Now the bottom example appears to be periodic, and you'll notice that I've gone ahead and filled in some values and I've done some shading. I see up, down, and back to a height of 0, and then notice in orange it appears to be that same pattern. I approximated that period a little past 6, so that appears to be about 6 1/4, very rough estimate. And then our amplitude, well, the midline, should always do midline next. Midline, -4 something to +4 something. That midline appears to be 0, and then midline up to the peak appears to be about 4.5. So that gives us an absolute, or an amplitude value of approximately 4.5. Notice these are approximations based on a graph. So that's it for handout 7.1. Hopefully this will clarify, at least in part, any of the questions you might have had as you tried to fill this out. Tune in soon.